Well, my friends, I will expose an article regarding or entitled Quantum Error Correction Will Enable Quantum Telescopes. Well, it's a very nice article because the researchers here from Australia and Singapore, they are attempting to make an application directly from quantum physics to to the telescope imaging. As you know, the telescope are the apparatus to watch outside the Earth. But if you don't know a nice calibrated apparatus for sure, but whatever you see is not true. Because there is a lot of light which is coming from the space. That's why you make the watching in the night because there is less perturbation and not in the day because the sunlight uh, will impede you to watch anything. So the point is that apparently you can see into exoplanets, meaning planets that are very, very, very far from here. You can see this by using a quantum application. What do? They apply a quantum error correction. I don't know if you remember, I mentioned before that the quantum error is relying to the noise that probably you will find when you are determining the quantum entanglement. So the quantum entanglement relies in the thing that the particle is moving in an entanglement two particles, yes. So the point is that in this coherence time, you don't know exactly if the particle goes up or down or a fraction in between. So before in the classical computing it was up or down, 0 or 1, but now it can be a fraction of it, or the two states at the same time. So meaning that this is a combination of the two states. So it makes the problem a little bit more difficult, but at the same time it makes it more usable. So in this sense, there is a problem which is based on the optical VLBI. VLBI means the very long baseline interferometry. The very long baseline interferometry is setting that you are not watching the truth about the information coming from the stars or the planets or the quarks or the pulsar. So the point is that you can correct this light, this information, because what you see from these uh, objects out of the earth is light. So if you are unable to interpret this light, you can determine what is the source of this light. So the point is that these researchers apply the quantum error correction to delete the perturbation in the optical VLBI. Yes? And they apply an interferometry technique which is simply combining the light that several telescopes are receiving. Yes? You have 1, 2, 3, 4 telescopes. They are receiving different angles of the light. When you combine all of it, as you are watching the same object, as you are watching the same the same planet, the same star, for sure, you can combine and see something useful about it. So the point is that it's not just combining, it's the thing that, okay, it can give you error. As everything in quantum entanglement, it can give you noise, yes? But the point is that by applying a simple quantum error correction, you can decrease the tolerance of this error and make more precise the determination of what the light is telling you about this planet. Let's say the wavelength, let's say the fraction of wavelength, let's say the distribution of the wavelength in a certain range of the optical spectrum, yes? Of the spectrum of light, of the electromagnetic spectrum, yes? If you can determine what is the distribution, for sure you can see, elucidate, yes, the atoms that are there are possibly this, the conformation of this planet is this, and the life that it has in the universe is this. So you can make conclusions, but it has to be precise, it has to be well confirmed, yes? So they apply the quantum error correction instead of a computer correction. So they make the correction and the light capturing instead of getting all the capturing and correcting after. So a very nice technique. How do they do this quantum error correction at the light that they are capturing? Because indeed they are entangling the light coming from the star, coming from the pulsar, coming from the black hole, and they are entangling this light with dark atomic state that it doesn't have radiation. As they are entangling, they are creating a quantum entanglement of the light coming from outside the Earth with the dark atomic state. When they get the collapsing of this entanglement and they apply the quantum error correction, they see, okay, what we have is this: the truth about the light and the distribution of wavelength in this light. Because it's not pure light, there are stuff that are happening in between, and I need to know, to see, and to make proper conclusions about what I'm seeing. Yes? So it's a very interesting strategy, because they are correcting on the light and not in the computer after they receive the light. So I think regarding what they report in this article is they make the first attempt, but they did not complete the entire evaluation. But the point is that theoretically talking is very promising strategy. And for sure, to delete the optical, the VLBI, the very long baselines interferometry error. Yes? So, just to mention this article, because it's one of the many applications that quantum computing and quantum entanglement are imprinting nowadays in the science, just by analyzing the light directly and making conclusion on it. Yes? So you can play with all these parameters and try to see what is the real truth, let's say, about a phenomenon which is emitting light. Yes, by applying just not the simple concept, but the concept of quantum entanglement. Yes, and the error correction is critical here, because, as you know, the quantum entanglement, because it's so sensible arrangement, experimental arrangement, is very sensible. So not deleting the errors can be crucial to detect nothing. So that's why there are several or plenty amount of codes regarding the quantum error correction, where you simply delete the noise that possibly is immersed there, and then you see, okay, no noise, I have the result, I see what is the truth. Yes? And for sure, they are getting very nice results, and the protocol is applicable not just in this system, but also extrapolated to some others that are referring the truth in science. So, well, I just wanted to explore this article because it appeared very interesting to me. I thought, okay, I will make it public to the people which is watching this content. I think it's very nice, okay? So if you feel very particular interested about this topic or some other that I have exposed here, for sure feel free to contact me and make me a question or something, and I'll be depending on you and try to discern what is the true in science, what can we learn about this very nice topic of quantum computing. For sure, I think it's gonna be very relevant for us in the coming years, and everyone should be at a certain fraction involved with this, you know. I thought it's very nice to share with you this knowledge, okay? Well, I hope to see you soon. Feel free to contact me, okay? See you. Ciao.